All right, so it's the last week of actual chemistry lecture. Next week we're just supposed to leave as a makeup week, so this is pretty much it for honors chemistry, believe it or not. And for this week, I want to get through the ideal gas equation. That is the equation that kind of puts together all the gas laws we've already learned and realizes that they all fit together in one big, grand, unified law of all gases. Now, these gas laws that we've been talking about, and this one that we're going to be building today, are called ideal gas laws, and this is the ideal gas equation. So I've been using that term, kind of throwing it around. What exactly is an ideal gas? Loosely speaking, I guess it's a gas that obeys all the gas laws perfectly. In the real world, real gases deviate from ideal behavior. So we use Boyle's law to predict pressures and volumes. In the real world, ideally every gas should have the exact volume calculated by Boyle's law. In the real world, different gases deviate slightly from that ideal volume, depending on the conditions you're working under. So there's no such thing as an ideal gas, but at least theoretically we can talk about them. What would make something an ideal gas? Well, for one, the molecules of the gas have no intermolecular attraction forces. So if you have two gas molecules zipping past each other, so here's molecule 1, here's molecule 2, zipping past. In an ideal gas, these molecules have no attraction forces, and so they're going to zip right on by each other. In the real world, of course, the nucleus here is going to attract the electron cloud there, and so it would actually deflect the path of the gas molecule. In fact, if the molecule was moving slowly enough, it would be deflected enough and stick fast to it, and when the molecules start sticking together, it's no longer a gas, it condenses out to form a liquid. So an ideal gas is one where it doesn't have any intermolecular forces at all, and there will be no deflection of the paths and no effect due to attraction forces. Obviously, that's unrealistic. All molecules do have those attraction forces, even if they're fairly weak. But the thing is, we're talking gases here. So in a gas, the molecules are extremely far apart, and so those forces aren't going to have much chance to operate on each other because they're so far away. Consider, even though Jupiter is a huge planet, how much does it attract you? It's way too far away, right? And the other issue with gases is they tend to be at high temperatures where they're moving very rapidly. So even if you have fairly strong forces here, the molecules are moving so fast that they may well be past each other by the time they had a chance to deflect each other very much. Okay? So there's that. In the real world, those forces do exist and eventually make the gas deviate from ideal behavior. The other issue is the gas molecules should have no volume. And by the way, these intermolecular forces become more important at slower speeds, in other words, lower temperature. The colder it is, the slower they're going, and the more likely the forces will pull them together to liquefy them out. It's why gases liquefy when you cool them down enough. How far down is enough? Depends on the nature of the forces. A gas with very strong forces will stick together even at pretty high temperatures. Water molecules stick together and liquefy well higher than room temperature. Whereas gases with very weak forces like hydrogen, H2 molecules, their forces are so weak you can get down real close to absolute zero before they finally start sticking together. Okay, so at lower temperatures, relatively speaking, these intermolecular forces make a gas deviate from ideal behavior and make all of our gas laws end up being wrong. The other assumption we make for ideal gases is that the molecules have no size. We treat all the molecules as if they had a size of exactly 0. Now, the reason for doing that is, and the same for the other one really, is because it simplifies the math. We could build equations with, calculating the volume. When we do that, we're actually calculating the volume of empty space. We could then also factor in a term to account for the sizes of the molecules times how many molecules we have. And that will give us a more accurate result, but at the cost of making our calculations much, much more complex. And since the atoms and molecules are so tiny, and in gases they're spread so far apart, Doing that, accounting for the actual size of the molecules, doesn't really improve our results to 3 or 4 significant digits anyway. We still get correct answers. When would this assumption fail? When you start packing the molecules together real tightly at very, very high pressure, where they're pushed close enough together where the size of the molecules does begin to matter. Then again, we'll see our gas laws deviating from ideal behavior. So notice at high pressure and low temperature is where the gas law, these assumptions begin to fail. And therefore the gas laws begin giving us incorrect results. There's no specific cutoff for that. It's just at some point the results start becoming more and more incorrect, and sooner or later you're like, this is no good anymore. They do have modified forms of the gas law here, but we're not going to deal with that. If we had, more time in the year, we would, but we don't. Now, let's look at combining all of our gas laws together. And we've already seen, I'll get rid of my beautiful artwork here, that what really it comes down to is PV over NT. Remember that. If you get rid of the NT, you get Boyle's law, PV equals constant. If you get rid of the P and the N, you get V over T equals constant, and that's Charles' law. So PV over NT equals a constant. Okay? Now, up until now, we've been using generic K for constant because the constant changed with conditions. With Boyle's law, if you use different temperature or a different sample of gas or whatever, you get a different K. But at this point, we've factored out all the possible things that could affect it. So what we're left with is a universal constant. So PV over NT equals a constant that doesn't change, a true constant for our universe. And so we give that constant its own name. We call it R. I guess a pirate got to name it. Okay? So PV over NT is combining Boyle, Charles, Gay-Lussac, Avogadro, all those guys into one law and equaling the true constant. Notice again, if you're dealing with Boyle's law, N and T are both constant, we can multiply through and bring them over and just make K equal to nRT, and so on for all the others. But doing it this way now, we come up with an equation that kind of includes all the gas laws within it. We often will multiply through by N and T and bring it up top here and get the equation that I showed you on the PowerPoint here, which now I can actually do the PowerPoint. PV equals nRT. Okay? The P is pressure, V is volume, N is number of moles, T is the temperature in Kelvin, R is the constant. Now, the value of that constant depends on what system of units we use. Often, well, obviously we use Kelvin for temperature, and obviously we use moles for moles. So, the units we often use are, we like to use atmospheres for pressure. Now, you could use other units, but we like to use atmospheres for pressure, and we like to use liters for volume. Okay, so R will have a different value in different unit systems. Our preferred system is liters, atmospheres, moles, and kelvins. And so we'll express our R in those units. Now, here's the thing we just define. Standard temperature and pressure. Now, standard pressure, you already know from the beginning of the chapter, is 1 atmosphere. Exactly by definition. Standard temperature is defined as 273 kelvins, 0 Celsius, the freezing point of water. So, together, these are our standard conditions. Standard pressure, standard temperature. We call that STP, standard temperature and pressure. So often we'll report our gas results at STP. Okay, so I go to the lab, and again, we would have done this if we had lab throughout the rest of the school year. We would have generated hydrogen gas in the lab, collected it under whatever conditions we were working at that day of pressure and temperature in the lab. Then we would have mathematically corrected it to what it would have been at STP. So we often correct our volumes to STP, what they would have been at standard temperature and pressure. And that way it's a simple comparison for everyone. Notice, if I know then the pressure and the temperature are standard, if I have 1 mole of gas, I could plug in, assuming I knew R, and find out the volume it would be. Or maybe another approach to that is I can take 1 mole of gas at STP, measure its volume, And then once I know that, and it's the same for all gases, that's what makes this ideal gas equation a universal equation. Given I know that, I can then solve for R. Well, it turns out that the molar volume of a gas, if you have exactly 1 mole of any gas at STP, it will have a volume of 22.414 liters. Again, that's called the molar volume of a gas. Any gas will do this. Take 1 mole of helium, store it at exactly STP, standard temperature and pressure, it would be 22.414 liters. Take 1 mole of nerve gas, and at STP, it'll be 22.414 liters. Okay, so given that we know that, you can now plug in pressure of 1 atmosphere, volume 22.414, N of 1 mole, and temperature of 273 kelvins, and solve for R. When you do that, you get R equals 0.0821 liter atmospheres per mole Kelvin. Okay, again, that's a constant. If we were in class, I'd have you memorize that constant. But there it is, you know it. If you look up R, you'll find it listed as other values as well in different unit systems. 8.31 in pascals or kilopascals, liters, moles, and kelvins, for example. Okay, but we're going to use this unit system. Now, to do a sample problem here, let's say I have a sample of fluorine. Doesn't matter what the gas is, it's ideal. We have the volume of 3.65 liters, the temperature 45 Celsius. I got to convert that to kelvins, don't I? And a pressure of 2.50 atmospheres. If I had given you a different unit, like kilopascals or whatever, you'd have to convert it to atmospheres first. So the question is, how many moles are present? Well, PV equals nRT. Plug in the pressure, 2.50, the volume of 3.65 liters. Looking for N, plug in R, plug in the temperature, 45 Celsius, convert it to Kelvin. And now do the math, you get 0.350 moles. This is easy stuff, isn't it? Okay, so here's an example to try on your own. I won't bore you with this because it's just plugging in, right? You can plug in the moles, plug in the volume, plug in the temperature. Don't forget to convert to Kelvin. Solve for the pressure. Okay, now, why bother with this gas law? Why not just use Boyle and Charles and whatever? Because in those cases, you always needed to know one set of conditions first. P1V1 equals P2V2. That's still true because P1V1 equals the same nRT as P2V2 does. So it still holds true. It's just that now with PV equals nRT, you'll notice I didn't need to know what the previous conditions were. I could just give you the current conditions of pressure, volume, temperature, and you can find moles. Temperature, moles, volume, you can find pressure. Out of pressure, volume, moles, and temperature, I can give you any 3 of those, and you can find the 4th one, given that you know R, which you obviously do now. So the ideal gas equation is very useful because you can simply plug in values and find the remaining value and not worry about, well, what was it before? Okay, that's still useful. Boyle, Charles, all those laws are still useful in their own context. But now we got this kind of one equation to rule them all that is useful in its own context. So I'm going to give you now some problems to try with this. Tomorrow we'll look at a variant form of this equation, and then that'll probably be the last lecture. After that, I'll just have you do more practice with it. All right, I will talk to you tomorrow.